Now, okay, the second talk. Thank you.
Excellent. So first off, I'm not Bhaskar Roy Bardhan. So Dr. Bardhan unfortunately cannot make it to be present here. So I would be covering for him for his talk, a portion of his talk actually. And this Dr. Bardhan's talk and my talk, which follows this one, have some overlaps, some similarities. So both of these talks are going to be, revolving around the idea of hybrid quantum and classical algorithms. So what do I mean by hybrid? So by hybrid, one means that the classical computers and the quantum devices are going to work hands in hand to solve a problem. Okay. So for instance, take example of GPUs, right? So GPUs are not like essential to solve a problem, but GPUs are used to accelerate or to help, speed up the computations one does in like machine learning or image processing and all sorts of things. So hybrid quantum classical model is along the same footing where most of the pre-processing and the post-processing is done by classical computer, but the hard computations, the computations which would take classical computers a lot of time, can be ported to quantum devices, and then classical computers interact with quantum computer, and quantum computer gives the answer of that hard part of the computation, and that's how this hybrid model works. So why is this hybrid model so important? It's important for many reasons. For the first reason and foremost is that the full-fledged quantum computers that we expect are not going to be available in 15, 20 years, depending on whom you ask. So in near term, what we will have is small devices which are noisy and intermediate. So instead of being able to do to solve full Shor's algorithm with fault-tolerant quantum computer, we can use these devices as accelerators, just like in the GPU model. So that's what this hybrid quantum classical algorithms are all about. And I'll be talking about some of those algorithms in Dr. Bardhan's talk and my talk. Okay. All right. Yeah. So the outline of Dr. Bardhan's talk would be basically quantum models, deterministic versus variational, and the basic of what variational circuits are in terms of hybrid quantum classical computation. Then we'll see a couple of examples, and then also we'll touch upon a little bit upon the quantum machine learning that one can maybe do using the near-term processors. Okay. So the quantum machine learning, this very nice, representation of the domains of quantum machine learning that one can do is that we know that there are two parts of machine learning. One is data, okay, and then there is processing of data, okay. So in the world between classical and quantum, what one can do is one can have classical data, classical processing, classical data, quantum processing, quantum data, classical processing, and quantum data, quantum processing, right? So classical data, classical processing, CC, that is already the field of classical machine learning. What we are trying to do now at the moment is take classical problems, classical data that we have, that we may generate from various, domains, and do machine learning, learn from those data using some quantum algorithm. So this is where we are, and that's what we would like to continue doing, at least for the foreseeable future. Okay. I have trying to advance slides. Yeah. So the quantum models come in two main, categories. One is deterministic quantum models, where we know we prepare a state and we know what the answer would be, and when the process finished, it gives us an exact answer. Okay, and then there is variational quantum models, where one doesn't have like a, a formal way of getting to the answer. But what one does is that one starts with some kind of guess, and then using optimization and gradual learning, one converges to an answer which may be approximate to the real answer we are looking for. So this is called a variational principle. Based on variational principle, these are variational quantum models. And the examples are, at the moment, like variational quantum eigensolver, variational quantum classifiers, and quantum support vector machines, and quantum neural networks on the near-term devices. Okay, so the motivations behind using variational quantum algorithms is that, first, it fits very well with the model of hybrid computation, where classical and quantum computers can work in tandem, and one doesn't need a full-fledged quantum device to do variational quantum algorithms in some capacity, right? So we know that classical computers are extremely efficient and on doing certain things, right? For example, we have like this amazing optimization algorithms. We have a plethora of codes and libraries which can handle data in a very efficient manner. So we already know like what classical computers are good at. So we will use classical computers for those purposes. And then we now know that there are some problems, like part of the problem that cannot be efficiently handled by classical computers. For example, computing, let's say computing a function that becomes very difficult for classical computer, that can be ported to a quantum computer. And that's how this hybrid model basically divides the labor between classical and quantum computers to achieve the best possible solution and like in a most optimum way. Okay, so variational quantum algorithm, one can like a generic structure. What that is basically is that one starts with some kind of training set of data, or an ansatz, a guess for your final answer, and then that is fed to this hybrid of classical quantum computer basically, and that ansatz input is fed to the quantum computer to compute a cost function, and that cost function is then sent to an optimizer, and this optimizer is a classical computer. Okay, and then after one step of optimization, the answer is again sent back to quantum computer for the next step. The cost function is computed again and then fed to the classical optimizer, and then this cycle keeps going on until we reach some convergence criteria, and at the end we get the quantum state that corresponds to the right answer, and probability distribution, and so on and so forth. So this model works very well for the NISQ devices, and there are some features of this model. Model is that these are very task-oriented programming of quantum computers. It's not like this would work for any problem that you want to solve with quantum computer. So they are like there are certain types of problems one can. There are only certain kind of problems that can be solved with these kind of hybrid model, and these are quite nice because in the near term, these like variational algorithms are like they provide the best hope for us to achieve what is called a quantum advantage. That is, by taking an example, a concrete example, where we can show that quantum computers do actually outperform, the best classical computers that we have so far. So these are like the best hope for us to show quantum advantage. Third is noise resilient and short depth circuits. So like these circuits for quantum algorithms are not very deep circuits, like they are short depth circuits. And then that's why, they are less prone to noise. Okay, there is noise still, but they are less prone to noise. And at the end, what we are doing is we are optimizing, and we have started with the guess anyway. So the noise in the devices are not so bad, don't affect the results too much. So that's one advantage of doing this. And in a way, variational quantum circuits are similar to what we have in neural networks, for example, right? You are given a data, you design a neural network with certain layers, and those layers have some parameters. And at the end, what we're trying to do is simply optimize over those parameters, right? So instead of having a neural network, what you have is a quantum circuit. Again, that quantum circuit will come with some parameters, and the quantum circuit just computes the cost function, and that optimization is done classically and fed back to the quantum device and so on. So that is a structure. So if you're familiar with training neural network, you can just think of quantum variational algorithms as similar to neural networks, but neural network replaced with some quantum circuit. Okay. All right. I am having trouble advancing the slides for some reason. Okay. So basically, this is again reiterating on the difference between the classical and hybrid classical quantum variation circuits. Here, basically in classical, you have some data, you compute some that correspond to some function f, and that gives us some cost function, and that cost function is then used to optimize and update the parameter, and this cycle goes on and on. In quantum theory, in quantum model, what you start with not just the data, but you start with some initial state over a number of qubits, and then there is a quantum circuit that acts on those initial state, and then you make a measurement, and that measurement gives you a particular state that corresponds to a cost function, and then the same thing keeps happening as in the classical model. So as you can see, this part here is different in classical and quantum, but update of theta cost is same in both situations. Okay, so there are some main components of variational quantum circuit, as I explained. First, we have to prepare a fixed initial state on which the quantum circuit can act. Then you have to design a quantum circuit, U theta. So designing this U theta is similar to choosing your neural network, right? So there are several prescriptions using which you can design a quantum circuit, and that is like one of the avenues where people have come up with really nice ideas which can be used to design a good quantum circuit depending on what kind of problems one is trying to solve. Like, for example, if one is trying to find the ground state of a molecule, there are certain classes of quantum circuits which work better. If you, for example, if you are doing QAOA, quantum approximate optimization, there are certain classes of circuits that work very well there. So just like in the classical machine learning, there is a trial and error. There is no one size fits all kind of rule here. For different kind of problems, we have to see what works best and then apply that to solve that problem. And then at the end, we make a measurement, and that measurement can be used to compute the cost function. That's how the variational quantum circuits look like. So this input, the variational quantum circuit that is called a circuit ansatz. Ansatz because we don't exactly know what we are trying to do. We're trying to find out a quantum state, right? A quantum state that minimizes the cost function, but we don't know what that state is, and we don't know how that state is spread over the parameter space. So what we do is just like in classical neural network, we come up with a guess of some layers, circuits with some parameters, and then we try to optimize over it. So that's what is being done. And then an important ingredient of this is cost function. So cost function is also it's not a universal thing. that one cost function is good for everything. Cost function is very problem specific. For example, if one is trying to look at a molecule, the cost function could be the expectation value or the mean value of a certain Hamiltonian, right? If you're looking at some graph size problem, then it could be just the like Hamming distance between the nodes and so on and so forth. So the cost function also changes from problem to problem. And then there is this training procedure, and then training procedure is basically choosing the classical optimizer well. It could be gradient descent or Adam or whatnot, and some improvements over it, how you can do that. Okay, so there are several examples. I will come to these, like a variational quantum angle solver, where one is trying to find out the minimum energy of an arrangement of molecules, depending on what the distance between the atoms are. So this kind of hybrid model has been used to showcase that variational quantum angle solvers can work in practice as well. And similarly, for example, quantum approximate optimization algorithm, like for example, this very famous problem of a maximum independent set, where let's say we want to find out, an independent set of a graph, that is like when the set of nodes which don't share an edge with each other. So those kind of problems can very well be ported to a quantum circuit, and using this quantum variational algorithms, that is by choosing an ansatz, cost function, and training procedure, one can expedite over the classical solution to get the right answer at the end. So how one can use variational algorithms in machine learning? So apparently I'm not an expert on this. I will just mention about the machine learning part here, that using variational algorithms, one can have quantum generative adversarial networks, and then one can do variational classifiers. Basically, just like in classical machine learning, you have classifiers. Using variational quantum algorithms, you can propose initial state, and at the end, one can get some classification, depending on some probability. And then there are quantum neural networks and variation encoders and so on and so forth. So, how would quantum machine learning in a variational framework look like? Just like I said a couple of slides back, that you can think of this variational quantum model similar to your classical neural network, where you give some input data, and that input data is fed through layers of neurons, and then at the end you compute the cost function and then do optimization. So here also, instead of feeding this input data, you prepare an initial state in this layer that is fed through a quantum circuit, that's the unitary circuit, and then you make appropriate measurement on these qubits, and then at the end, depending on what outcome you get in a measurement, that corresponds to an output vector y, which can be used to compute the cost function. And one has to do this over and over again, so that one has enough samples to get the mean value of cost function. So that's how QML in a variational framework would look like. So for instance, using that variational classifier, at the end, after measurement, the cost function could map the initial, all these parameters to plus or minus one, basically classifying data into two different domains. And similarly, one can have quantum enhanced support vector machines, where you use quantum circuits at the end. And this is again reiterating over the similarity between neural networks and quantum neural networks. So again, like instead of just like having classical neurons, one can, like have a cascade of, parameterized and unparameterized layers. And after using measurement, you can have a quantum framework for neural networks. And you can just you can further use this to do autoencoders as well. So this was the content of Dr. Bardhan's slides. I will now quickly move to my part of the talk. So if there are any quick questions, I guess I can take those at the moment on Dr. Bardhan's slide.
On the optimization that you mentioned in certain steps here, they are all classical, right?
Yes, optimization is done
all classical algorithms.
Yeah.
Now, some optimization problems can be done by mapping them to Ising model, but not all of them.
Right.
Right? Now, is there a way to borrow from the quantum approach to do this mapping better, to make this mapping easier? Because when you talk hybrid, I can think about hybrid hardware to hardware and software to software. And then in that kind of matrix, I can take diagonals and do software to hardware, hardware to software. Okay, so that matrix is actually quite interesting, and I like to see some expansion of that in this discussion of hybrid, because hybrid concept is very exciting by itself.
Right. So all the ideas of hybrid, when it comes to quantum and classical hybrid, the hybrid model is exciting only when the quantum hardware is involved, right? Software, definitely, software has to come. The classical hardware and classical softwares have to come into the picture, and there has to be quantum software that can let the classical hardware interact with the quantum hardware. That is definitely true. But what is the essential piece in this quantum classical hybrid model is the quantum devices, basically. So I don't know if I answered your question or your comment well, but this is what my thinking is.
Yeah, thank you. I believe that in this kind of space, there is something missing in the input of innovation, because there are some gaps here. If I think in the general matrix of all these interactions or cross-field fruition, there is things that are called for, and yes, your answer is we are limited to what we are limited right now, and I accept it.
Right.
But there is room for expansion.
Yeah, there's certainly room for improvement and expansion always. So I mean, if you have some ideas, I'm sure they will be welcomed quite well.
Yeah, working on it. Yeah.
Yeah.
Okay. Good. There are some other questions. So given some context problem, why would you choose VQE or QAOA?
So what's the question again? Sorry.
Given some context problem, why would you choose VQE or QAOA, Variational Quantum Eigensolver or QAOA?
I mean, these are the most studied problems when it comes to variational algorithms, and at the moment, and they are the most well established. There are numbers of papers on variational quantum eigensolvers and QAOA, and more so because these two problems represent two different classes of problems which could be which could be used to solve some real life problems in future. So that's why these are exciting. For other domains, like for example, applying quantum computing to finance and stuff, those require like much better hardware, fault tolerance, error corrections, and so on. So that's why these two kind of problems are more important, and you will keep hearing about these two problems everywhere you go. That every talk you hear that has to do with NISQ. Does that answer your question?
Yeah, I think so. So maybe there will be some follow-up question. There's one more question. Can you comment on the state of getting data into and out of a quantum computer? So this is a question from Shahin, I guess. So
yeah, can you comment on the state of getting data into and out of a computer?
Yes, that's correct. Mm-hmm.
I mean, I can't say I understand the question well, but I'll just explain how the quantum processor works as when it comes to data. So the quantum devices are not designed to take classical data directly. What one needs to do is that encode that any classical information on classical data that you have in terms of quantum data, quantum state. And the best way to do that is basically you have, let's say, a bunch of qubits. You prepare those qubits into an initial state, and then change the state of those qubits by some parameterized layers of gates, quantum gates. And then following that, what you do is you make measurements on those qubits and see after applying those parameterized gates, how the state has changed from the initial state in which you prepared the qubits in to a final state that you have after measurement. Okay, so this is the whole process of how a quantum computer would process the data. So you have a classical data, you embed into a quantum state, you do some operations on the quantum state. At the end, you make a measurement, and that measurement gives you, that measurement can be used to compute, a mean value or expectation value of some cost function or Hamiltonian. I hope that clarifies.
If I may, the question really is about the encoding of the data. How long does it take to encode the data into the quantum state? And when you do the measurement, how long does it take for that measurement to translate back into the classical computer? So the question really is the input and output into and out of the black box of a quantum computer. Yeah,
I mean, I think that part is not so much time taking, because when a quantum computer, when you make a measurement on the quantum computer, the state that you get out of it is actually a classical information. It's a classical data. It's just a bunch of ones and zeros. So those can be directly fed into your classical optimizer to do measurement.
How about on the way in?
On the way in, again, that depends on the kind of hardware you're using. There might be some latency in in preparing the qubits or holding on to the prepared state. But as far as my understanding is that that is not also so much time taking either.
Okay, thank you.
Right. There's one more question. Is there an existing hybrid solver that is shown to outperform the corresponding classical solver?
No, we don't. I mean,
okay.
The hope is that when we scale up the system to a higher, number of qubits, like 200 and 300 and so on and so forth, we may be able to see some advantage, some quantum advantage. So, but at the moment, there are theoretical results that, quantum computers might be able to, outperform even these quantum variational algorithms might be able to outperform classical computers for certain regime. But at the moment, we don't have an experiment or like, an example where we can showcase exactly, let's see, this is what is happening, and we cannot do that. But the classical computers cannot do that. I mean, there are other there are quantum supremacy experiments which are different, right? Those are not based on any variational algorithms. Those are very esoteric problems, very specifically designed problems which don't have to do anything with any practical use, right? So that is a separate issue. But as far as the variational algorithms are concerned, to get a quantum advantage. So that's how, I mean, in my mind, for how I understand quantum advantage over quantum supremacy, is that quantum advantage is something where we can show that we can use quantum computers to do something useful faster than quantum, classical computers. But quantum supremacy has to do with much more. I mean, it has to do with probability of like provable quantum advantage. It has to do with the asymptotic features, like when you scale the system, and then due to exponential scaling, classical computers are just bad, and the quantum computers will be able to solve those problems. But in quantum advantage, even if you are not able to get exponential speed up, but some kind of advantage in accuracy, or even some kind of polynomial gain in the speed, that would be good enough. So yeah, that's my thinking on that.
Okay, great. I think we can go on to the next part.
Next talk. Okay. So a lot of what I'm going to talk about, I already have introduced, at least the initial material in Dr. Bardhan's talk. So I'll quickly go over the initial slides and then talk about some of the things that I have been working on lately. So in the previous talk, we saw, or we discussed, what variational quantum algorithms are, right? And they are quite good, and they offer the promise to get a quantum, to showcase a quantum advantage in near future. But what all things we can do to improve upon the existing techniques is what I'm going to talk about in these talks, these slides. Okay, so variational quantum algorithms, as we know, they are very problem-oriented quantum devices, but at the same time, they also allow a certain degree of flexibility in the paradigm, just like in neural networks. Using neural networks, you can, solve all sorts of problems. There are different kinds of sorts of problems, because all you're doing at the end in neural networks is that you have a bunch of parameters over which you are optimizing. So this paradigm that you start with an ansatz, you have a quantum circuit, you do optimization, and you get the answer at the end. It can be used to do many kinds of optimization problems. Third, they are short depth circuits, so they are less prone to errors, and they don't require fault tolerance. So they are quite well suited for the near-term quantum devices. Okay, and there are many applications being explored at the moment, starting from finding ground states of molecules in quantum chemistry to mathematical problems such as system of equations and machine learning and so on and so forth, right? And as we saw in the previous talk, variational quantum algorithms are based on a quantum classical hybrid model, where you have input, and then you do processing, or that input is encoded, fed to a quantum computer. The quantum computer gives a state, and that state is used to compute the cost function and do optimization in classical computer. And then this cycle keeps happening until we get to some convergence level. And the good thing about this is that we already have quite an advanced optimization algorithms in the classical computing. And all those can be used. All those can still be used to do optimization, but doesn't really have to look for a quantum optimization to be able to do something useful at this moment. So the examples are VQE and QAOA, which are like the forefront examples at this time. So that is like finding ground state of molecular Hamiltonians and max cut problems and so on and so forth. All right. Now, so variational quantum algorithms have like four main components. One is input, the ansatz that one chooses, the classical optimizer that one is using, then cost function, that is a cost function that defines the distance between the target and the input basically, and the output of what is the output of the variational quantum algorithms. So there has been a lot of work in choosing different kinds of ansatz, and that there's a plethora of work in showing that there are certain kinds of ansatz which work quite well with molecular Hamiltonian, and there are some which work with max cut problems and so on and so forth. So I'm not going to touch on that. What I'm going to talk about today is
Sorry. What is the definition of ansatz, please?
Yeah, so ansatz is like a guess of the, for example, at the end, what you want to find out is that what is the state, what is a quantum state that minimizes the energy of a molecular Hamiltonian, right? But we don't know what that state is to begin with. Okay, so what we're going to say is that, okay, I don't know the state, but let me write a function of the state, like the state to be parameterized by 10 parameters, theta 1, theta 2, all the way up to theta 10. And these parameters, theta 1, theta 2, theta 10, are encoded in the quantum circuit. Okay, and then what we are going to do is we are going to find out the best combination of these thetas, which minimizes the energy. The final answer may not still be the exact ground state we are looking for, but it would be as close to the ground state as possible. So the ansatz simply means a guess of this final state that we are looking for. And that's where it becomes quite interesting, that if you know something about the problem already, right? For example, if it was just a hydrogen atom that you are trying to find the ground state of, then you know that the state is going to look like Gaussian, right? So similarly, we know quite a bit of physics about molecular Hamiltonians. So we choose the initial guess of the state to be similar to what we already know, that we know that the state should behave more or less like this. It should be more like Gaussian, and it should have some parameters that changes Gaussian in some way. So we start with a guess, and then we tweak our initial guess. We correct our initial guesses using the classical optimization. Does that make sense?
Yeah, thank you, sir.
Okay.
It's like Bayesian statistics.
Yes.
Thank you.
Right. Yeah. Similar to that. Okay. So what we are going to talk about, that how we can make improvements on variational quantum algorithms by playing with the classical optimizers that we already have, and what we can do about cost function that are already given to us. For example, can we do anything further on the cost function to get some like better convergence or better results? So okay, so improving optimization. So if you recall the standard gradient descent method, what you do is in each step of optimization, this parameter theta at t+1 step is modified by like theta t minus this eta, this is called the learning rate, and the gradient of the loss function or cost function, right? This is like the standard gradient descent method. In this method, this is like if you have just two parameters, theta 1 and theta 2, then let's say theta 1 and theta 2 are like correlated with each other in some way, and this is like the contour of the loss function. Then the standard gradient descent just tries to move to to the lower loss function or lower cost function without knowing anything about the correlation between theta 1 and theta 2, right? Because this gradient is not scaled with anything that has information about the correlation between these parameters. Then came the natural gradient descent method, where what one does is that say, okay, instead of just moving in taking step like one would do in Euclidean geometry, why don't we use this information, how theta 1 and theta 2 might be related with each other. So in this case, for instance, like if they can be mapped to phi 1 and phi 2, where instead of just doing random, like taking random steps, what we do is we try to take steps in the direction of the lower value of loss function. right? And this is what is called the natural gradient descent method. So what one does is that computes this Fisher information matrix that knows about how phi1 and phi2 or theta1 and theta2 are related with each other, so that helps the taking the gradient descent in a direction where their local minima might be, okay, using the geometry, using the information about the geometry between theta1 and theta2, or the parameters. So this is the classical way of doing a natural gradient. Interestingly, one can generalize this to quantum regime, albeit by, instead of using quantum Fisher information, what one needs to compute is this Fubini steady metric tensor. So this G is a quantum generalization of the Fisher information. And it turns out that using this, we can have a quantum natural gradient method to take to compute the next step in the optimization process. But then the question is, in classical theory, we know how to compute quantum Fisher, like Fisher information. But in quantum, how do we compute this Fubini steady metric tensor? It turns out that computing this is classically hard. So interestingly, there has been work which shows that this metric tensor can be computed using quantum device. So in addition to using the quantum device to compute loss function, what we are doing is we compute L using a quantum device, but we also use quantum device to compute G, this quantum Fisher information, or this steady metric tensor. And then using that, we improve the optimization process. So I'll just show you one example where we have used the quantum natural gradient method to improve over the vanilla gradient descent methods, right? So this is an example of like an Ising model. These both are same figures. Sorry, that's okay. So this is a 8-qubit Ising model that we are looking at, and relative error. And on x-axis, it's the optimization steps. So vanilla gradient descent method is shown by green right here, right? And it turns out for Ising model, if we are looking at the quantum natural gradient, then if we look at only the diagonal terms of the quantum Fisher information, it doesn't improve the results much, which is counterintuitive, because usually one would expect, there are examples where just looking at the diagonal elements gives you improvement over the gradient descent method. What we found, however, is that if we use a full quantum natural gradient metric, then there is an improvement. That is, like it converges faster, and so one would get better results using quantum natural gradient. So in this way, using quantum natural gradient, which employs the quantum device to compute quantum Fisher information, we can improve the optimization. So in this way, so this is an example of how quantum device can also enhance the optimization process, not only the computation of loss function, but also the optimization. Okay. All right. Now let's think what we can do with the cost function. So usually, I mean, when we come up with a problem, the cost function is already defined, right? And the way we work with it is that the quantum circuit gives us some samples, and let's say those samples follow this kind of distribution given here. And what one does is that we use all the samples, or like whatever samples given by quantum device, to compute the cost function. Like basically, if we knew, like in an ideal world, if we knew the distribution of samples coming from quantum device already, and if we knew how to efficiently, sample from them, just sampling from the whole distribution and computing the cost function would just give you the cost function, and then you could proceed with the optimization. However, in recent work by in this paper shows that instead of using the whole distribution, right, for some kind of Hamiltonians, like diagonal Hamiltonians, if we just use the tail of the distribution to draw samples and compute the mean value of the loss function, then one would be able to, one may be able to find the minima of loss function or cost function much faster. Okay, that is the statement. And now let me just show you how to get an intuition why that should be or that might be true. Let's take an example of this quantum circuit right here. Very simple. Just 2 qubit, Hadamard gate, C0, and Y rotation. And for a diagonal Hamiltonian, it turns out, like, for example, the cost function corresponding to this whole distribution basically is cosine square theta plus sine square theta. But this is just 1, right? This is constant. So, however, if we just take like a 50% of the distribution to compute the mean, the cost function changes. Instead of this, it has sine square theta by 2, right? So so this shows that drawing samples from partial distribution changes the landscape of the cost function with respect to the parameters that we are looking at. Okay, so for instance, if you look at this plot here, on x-axis we have theta, on y-axis we have C alpha theta. For alpha equal to 100%, right, that is alpha equal to 1, the cost function is just 1, no matter what the value of theta is. But for alpha 0.5, the cost function takes all the values between 0 and 1, right? So for the partial distribution alpha 0.1, one is able to explore more space of the parameters. Okay, so it just tells us that, okay, if we just use a partial distribution, then we may be able to find the local minima which were missed by taking a look at the whole distribution. Okay, so this is the basic idea why this sampling from tail of the distribution might work to get to the local minima faster. Okay, so, and to show that it works, we took an example of maximum independent set problem, where we generated a random graph of size 40 nodes, and it turns out that, again, for alpha equal to 1, the cost function doesn't change much, right? But if we just draw samples from the tail of the distribution, for lower alpha, one is able to converge to the results faster, much faster, as compared to if you take samples from the whole distribution. So the result is that tail of the distribution leads to faster convergence. So in this way, improving the cost function in terms of like just looking at only the partial distribution can also improve the variational quantum algorithms. So this is another example where how we can improve the already existing paradigms of variational quantum algorithms using either improving over the cost function or by taking advantage of quantum natural gradient.
Do we know why it works?
Yeah, so that's what I tried to explain in the previous slide, that the argument is that for diagonal Hamiltonian, the mean value being computed from the whole distribution, right, is not exactly the same as computing from only partial distribution. So these two computations are actually, although the function of the form of the function of the cost function is same, these two distributions are fundamentally different. And that's why they are able to explore, the parameter space differently. Just like in previous example, here for alpha equal to 50%, for different values of theta, C alpha theta was different, like from 0 to all the way up to 1. But for alpha equal to 100%, C cost function was constant. So all value of theta would be like, would give you the same cost function. However, for example, theta equal to 0 would give you cost function 0 here. So by looking at the partial distribution, you would be able to explore the space of the parameter, which is missed by the whole distribution, like by looking at alpha equal to 100%. So far this has been shown only. Sorry,
one of the things I would say is to look at it slightly differently than from a gate-based, we're looking at hardware gate-based and all that. One of the other way to look at it is as a wave. And if you look at it a whole wave, which is what you were saying, sine squared, cos squared theta plus cos squared sine squared theta is equal to 1. That's the whole wave. But if you then look at the one phase of the wave, because wave has both constructive and destructive interference, that's when you really get that, that difference. I mean, I'm just trying to show it from a slightly different way.
Yeah, that's also a good perspective to look at it. Yes, I agree. Thank you. Okay, so I would just like to summarize here that there are potential pathways to improve variational quantum algorithms, and we are working on it. And then there are interesting questions one can ask, like, can we combine, the ideas of, looking at different cost function with improving over optimization to get even faster convergence. And then the results shown here in particular for the partial distribution or tail of the distribution was for diagonal Hamiltonians. So what about non-diagonal Hamiltonians? Like, for example, Ising model, when there are like sigma x and sigma y terms, can we get improvements over there or not? I mean, those are also kind of questions we would like to answer. And then we would also like to know, like, what other kind of problems can be solved faster or can benefit from these kind of improvements. So this is a work in progress, and I would like to stop here and open the floor for questions. Thank you.
Okay, thank you so much, Brajesh, for this great presentation and for the answers. I believe the chat is quite intense, actually, and there are some questions. So first of all, let me go first to the first question. Just a second. So Mr. Itmar asked if that is the ground state like the equilibrium of the quantum system itself?
Yeah, you can think of it that way. The ground state is basically the state that corresponds to the lowest energy of the quantum state. So the one important difference between classical world and quantum world is that in classical world, the lowest energy is 0, right? But in quantum world, that is not true. The lowest energy is not 0. There is some energy gap. And that's why it becomes quite hard to find out what that lowest energy is. In classical world, we already know the answer. The lowest energy is 0. But finding the lowest energy in quantum systems is a hard problem.
Are you saying it's below 0 Kelvin then?
No.
Because it cannot be.
No, not below. Above
energy, no temperature.
Energy is always positive.
Yeah, so this is why, I think when you say 0, I think the absolute minimum that anything can go is 0 Kelvin. And I think even in classical world, people do understand. I mean, unless which measurement are you applying? If you say Kelvin, there is nothing that can go below 0 anyway.
Right. So yeah, that is true. And so what I'm saying is that you cannot go below 0, but in quantum system, what is the minimum you can go to? Right. I mean, for example, if I'm looking at, just take an example of a harmonic oscillator, right? I mean, let's not go to like statistical system yet, just harmonic oscillator, pendulum, right? A pendulum, the lowest energy of that pendulum would be zero, like zero kinetic energy, zero potential energy, right? But in quantum, a quantum harmonic oscillator, the lowest energy of the oscillator is not zero, it's something, and that is called the vacuum energy or the energy gap. And a priori, I mean, it's not known. I mean, and that energy gap is not universal. For different systems, the energy gap is different. And the more complex the system is, the more difficult it becomes to find that ground state energy.
So I think, you know, because you were referring to earlier in your talk, when you were talking about chemistry, hydrogen atom. So one of the things, obviously, I wrote over there is to do with, you know, the lower state of the atom itself. So you're moving from an excitation state to a lower state, which was in relation to chemistry. And that's why I mentioned 0 Kelvin. But I think you rightly summed up, you're essentially talking about the difference between potential energy and kinetic energy. That really is the base. Thank you.
So the ground state, is it the global minimum? Because 2 minutes or 3 minutes ago, you mentioned local minimum, and that confused me.
Yeah, so ground state is global minimum. That is true. But
okay,
you see, any optimization algorithm is not guaranteed to find a global minimum, right? What we do in optimization is we take the minimum of all local minima that we find, and that we say that is probably the global minimum.
I would say, I mean, shouldn't it be local minimum, because you are actually concentrating on that very experiment in that frame of reference. So that frame, that energy you're referring to is within that frame of reference and therefore local to that frame of reference.
Right. So a global minimum, a ground state is both local and global, right? I mean, just by saying that it's a global minimum, it also is a local minimum just by definition. But to say that ground state is global minimum means that, for example, in a harmonic oscillator, you can design no harmonic oscillator with that mass, which will have lower energy than that ground state. That is just forbidden by the law of quantum mechanics.
Okay. Another question by Mr. Itmar Halvi. What is the Fubini study?
Oh, Fubini and study the name of two mathematicians who generalize the quantum, the Fisher information to quantum systems. It's just that. Fubini.
So just, you know, the quantum version of Fisher information matrix.
Yes, right.
Yeah. Okay, thank you. Okay, most of the chat here is simply enough, you know, a debate or just questions to Aruza and her presentation and previous presentation. Actually, I have a slight small comment regarding, you know, encoding classical data in general with any quantum computer that we have right now. First of all, regarding, you know, the perspective of traditional machine learning, let's say that all types of data, like videos, text data, or numerical, or whatever it is, we convert it into somehow, you know, numerical values. That is the first thing. And after that, we do some feature engineering so that we can either, you know, reduce the dimensions or, for example, increase its you know, its richness or its expressibility, or, you know, to make it more expressive on its own, so that we can use a very simple model, because whenever you can use a simpler model, that will be like the best solution regarding you know, the business, I mean the cost of the business itself, or even the computational complexity of the model. Okay, and that's it. The same thing we can apply it to a quantum computer, which is right now most of or the most important step in any quantum machine learning algorithm, especially in the variational algorithms, is to have like a better encoding. Because if you have a better encoding, then the variational ansatz at the end will be very small, and that is what we need for the NISQ era currently. That is the most important thing. So choosing a better encoding is like choosing like 90% of the performance of your quantum machine learning model. Okay, and another thing here is that regarding the sample complexity, superposition does not mean that you have like a superior way of encoding your data. Perhaps if your data is very complex, or it doesn't have like a lot of features to represent the internal structure, then superposition may or may not help you in this situation. So it's a try and error situation, and it's not like there is no general rule here to say that okay, we can say that superposition is like will increase the complexity or decrease it. It's not like this. And regarding a question here that says if we have like 1000 by 1000 matrix, for example, that would mean like we have 1000 samples and 1000 features. How can we encode something like this in a quantum computer? So regarding this much of data, first of all, you can use like a classical neural network, an autoencoder, so that you can reduce the dimensions of your data, for example, like up until 20 dimensions or 10 dimensions. Then you can use the regular encoding of angular encoding, or do any fancy encoding using ZZ interactions or Pauli interactions, whatever you would like to name it, or you can use amplitude encoding, but that would require like a very powerful quantum computer, which we don't have right now. But that is the only way of encoding the complete 1000 features in a single iteration or in a single way, without repeating or reinitialization or doing any reinitialization for the quantum system. So it's just a hardware limitation that we have right now. But at the end, choosing like a very good way of preparing your data is the most important step, especially in quantum machine learning. And that is like my comment regarding this matter. And perhaps one final question here: isn't the idea of moving classical data into the quantum realm like the concept of analog versus digital data? There will be some type of converter needed on each side. I think perhaps I can leave this question for you, if that's okay.
Yeah, I mean,
so, let me say it one more time. Just a second. Where is the chat? Okay, so isn't the idea of moving classical data into the quantum realm like the concept of analog versus digital? There will be some type of converter between digital to analog or analog to digital converters needed on each side. I think that at the end, for example, like in superconducting qubits, we are using the how can I say
microwave pulse generators.
Microwave pulses. So you're actually, yes, you are converting in some situations analog to digital and digital to analog. So I think it's like a hardware level question than like away from the algorithmic world. But what do you have a say on this?
I mean, yeah, so it depends on the hardware. Like you correctly pointed out, for superconducting qubits, is the microwave pulses that are used. For others, like optical signals are used, lasers are used, and so on and so forth. So that's right.
Okay. I think there is one more thing. Well, there's two things I like to add here. First of all, what Kareem said earlier, that superposition does not offer an inherent advantage. But the whole idea about quantum computer is the superposition, because you don't have a qubit without superposition. So when you're talking about moving from a classical workload to a quantum workload, you are talking about superposition, because without that, there is no quantum computer. And I think there was one question here with regards to, it says about this Ahmadi's law, where somebody's mentioning about QC is not merely a quantum computer with more cores. And there is an example which I really like. It offers a slightly different way to visualize this. And it goes like this. Imagine you have a maze, and there is a path from maze that you have to calculate from one place to another place. One place you enter and the other place you exit. If you were to follow a sequential classical computer, you will have to try each and every path, right? But imagine with a quantum computer, you have a bucket of water that's released and appears at all the points at exactly the same time. And that's the exponential advantage that you have. It's not as good. It cannot be compared with anything classically, because this is happening because when you look at the quantum entanglement, everything is happening at one instant of time.
I just want to interject here because I brought up Amdahl's law, and I didn't mean it in its interpretation for parallel processing. I meant it in its general interpretation when you have a totality of a task. And because the case in point here was a cooperation between classical and quantum computing, where there's an iterative process, there's a part that the quantum computer is doing, and there's a part that the classical computer is doing. And if the part that the quantum computer is doing is reduced to zero, the classical part is still going to take over, and that can be wonderful. That happens with GPUs all the time. But if the process of getting the data into and out of the quantum computer is not worth the effort, that can be an issue. This was the issue with GPUs for quite a while, for quite a long time, where you needed a particular use case that had sufficient residence time for data once the data made it over to the GPU. And it needed to stay there long enough for you to actually gain some benefit before it had to come back. So that was the motivation for that question.
Yeah, and I agree with Shaheen completely that those kind of situations might arise, and just like in GPUs, right? And at the end, you might be able to solve those and get some advantage. So it's a playoff between how much time it really takes to load on and load off the data and process it, and whether that is worth doing. Considering the whole problem. So
really the immediate question for me was that what is the impact of that on the use cases that are suitable for quantum computing right now?
Right. I mean,
just like with GPUs in the early days, you really needed like a 2D convolution or a matrix multiply for it to make sense. So what kind of an application, does it need to be the kind of application that the input data set is really minimal and the computation is, how does that mean? That was the motivation, really. Thank you.
Yeah. Good.
Okay. Regarding this superposition thing that I said, what I meant is that applying a Hadamard is just like rotating your state vector in the block sphere, for example, if we are talking in the case of a single qubit. So what if your data points is not distributed in a very well or in a good manner using a Hadamard transformation? So that is what I said by when you do a superposition, it doesn't mean that you will have like a good separation for classification or for a regression problem. So choosing the proper encoding at the end is the most important step. So perhaps superposition will be a good start for you. In other situations, it will not be good. So it depends mainly on the data. It's data dependent or problem dependent. That is what I meant by that. Superposition is not like the most important thing, or I didn't mean that it doesn't give you some advantage. Of course, in some in some algorithms like Grover algorithm or in Shor's, of course, Hadamard is very important transformation. But in the realm of quantum kernels, for example, it's it's completely problem dependent. We cannot say that okay, superposition will be good in this case. That is not. I haven't seen a paper that says this encoding is like the general encoding that we can use in any case. No, each data set has its own distribution. Yeah. We should be very careful when we choose the right encoding for it.
So Kareem, now I'll have to leave and now. So I
just have one question, please, if that's okay. Just wanted to ask your view. So I wanted to ask you, I mean, and just a view. I know there's no answer to this problem. I mean, what are your thoughts on? I mean, has anybody looked at, because I know that astronomers, they work in a different field, and chemistry people, they work in their domain. My question is regarding, has anybody looked at the problem of the information loss at the edge of black hole and the information that's coming out in terms of light, to apply a machine learning model or a neural network model to that to actually recover that information? And because I'm looking at a project where this can be reapplied back to information security, for example, completely different domains, completely different problems, but something that is very amenable to sort of quantum machine learning. Any of your view on that?
I mean, I'm not aware of.
Because if you look at,
but
I mean, even
I would
if
have
you
to think
look at,
about how that can be done. I mean,
Sure.
on the top of my head, I'm not sure how would that play out.
Right. Okay. Thank you.
Okay. Thank you. So thank you all for joining and listening to me. I will take leave now.
Thank you, Brajesh.
Thank you. Bye.
Interesting talk.
Thank you.
Thank you, everyone.
I have a question for everybody. And this is, since superposition was mentioned as a key element of quantum computers, whether advantage or not, the question for now, until the quantum computers will be really viable, maybe we can find a tricky way to push superposition to the classical computing. Is this too daring?
What do you mean by this?
It's already happening. It is already happening in, if you look at all the simulators, you look at the Q-Sharp simulator, you look at, even when you run an IBM simulator, you will find that behind the scenes, it's not that you will get access to an actual quantum device. Sometimes you get a simulator which does precisely that.
Can I get any reference to that? I'll be very interested to follow up or learn more about it.
I have sent a link on the chat here regarding IBM Quantum. Okay.
That's appreciated. Thank you so much.
You can find a lot of resources that you can start with.
Thank you. Thank you.
You're welcome.
Appreciate it.
And Henning, are you still online? Can you give us some feedback about this talk?
Yeah, I certainly enjoyed the depth that he went into to discuss improving the gradient descent method for variational eigensolvers. And I think that the one question I came up about the challenge of when it actually is worthwhile to have a hybrid model, because you have to have the communication between the quantum bit and then the classical side, and that's a huge practical problem because you can't have the classical computing part too close to the quantum processors, because the latter typically operated close to absolute zero and they need to be absolutely shielded. Whereas, of course, if you have conventional computers, they run very heat output, and they produce a lot of electromagnetic noise, and you can't have these two pieces very close together. And we all know these kind of inverted Christmas tree kind of pictures of the way that these superconducting chips are kept in their cold storage. So you have all these elaborate steps. Basically, as they go down this Christmas tree layer by layer, they get colder, and you are stripping out noise from the cables that are connecting the outside world to the quantum chip. So it's really quite elaborate to get the data in and out, just from engineering feet. And so that is really something that from a practical standpoint, I think is going to hamper the hybrid model. If there's theorists like Scott Arison also who basically kind of scoff at the concept, because they're basically saying, well, why do we need a hybrid model to begin with, since a quantum computer, a real quantum computer, can of course also perform classical computations. And if you can do a qubit, you can have a classical bit. So their stance basically is, well, this is all kind of just dancing around the fact that we don't have real quantum computers yet, because if you had real quantum computers, you would just push the classical part into the quantum processor as well. And it relates also back, or relates back to the question that was in the chat about quantum RAM, right? I mean, if you had a real von Neumann architecture as a quantum computer with quantum RAM, all this kind of processing would take place in the quantum space. So hybrid computing really is kind of, yeah, it's the way to try to squeeze value out of these near-term noisy systems that we have right now. And there's going to be, I think, from my perspective, there's going to be a limited applicability to it. It is going to be mostly probably in machine learning when you can really push most of the optimization into a one-step quantum processing on your quantum computer, and you don't have to do these callbacks to your classical processing all too much, because it's just costly to get this data in and out. So that's just my 2 cents.
I think with regards to Henning, what you just said, so if I'll take you back to a bit of classical thing, what happened. If you remember that originally when processors were, kind of getting built, you hardly used to have, a processor cache. You had L1 cache, you had L2 cache, and now a lot of stuff is done closer to the processor. So my view is that originally you will access quantum computing through the cloud, through a cloud API. You'll feed it into using high photonic channels. You'll feed it into a classical computer, do the classical load over there, go back to the your quantum computing workload via the same channel. And this is how the whole orchestration will really function in the beginning, because of the cost involved. And quantum computing will, real quantum computing will not be available to one person to use it for, just like we use our laptops today. So that's how initially it will work. And then as these quantum storage devices will appear in the market, then we'll start seeing your quantum RAMs, your quantum caches. Those will preserve the data, and also by this time we will also have a good level of insulation, but that's a bit far away. But in the meantime, we will end up having the same journey as we started with classical computing. That's my view.
Yeah, I agree. There's a lot of analog kind of development in terms of this is from a historical perspective. Also, how we started out classically with analog computers. So the D-Wave essentially you can think of as an analog device that because it doesn't have any error correction really. It's going to take quite a while for all these different models to shake themselves out and to see who the winner is going to be. And of course, everybody, as you mentioned, is aiming to have their devices in the cloud and to eventually monetize the investment, which has been, of course, considerable in these quantum devices by charging a premium. And IBM is already doing this essentially with their higher end chips. But of course, I mean, the killer application is still missing, right? I mean, everybody is looking for this killer application with you can say, here there's this first case where you need to have a quantum computer in order to solve a real world problem that really translates into big monetary benefits. By the way, I also posted another link for quantum simulators on the chat. So there are quite a few open source quantum simulators out there.
Thank you.
All right, if there are no more questions, I think I'm going to drop off as well. Thank you everybody for attending, and thanks Helen again for making this possible. And it was a couple of fascinating talks.
So if anyone wants to stick around, please feel free to discuss anything you like. This is a great chance, and thank you so much for your participation. You can
again, thank you.
Thank you, Helen. Thank you.
Thank you, Helen, as always. Thank you, Deb. Great job.
Thank you all. Thank you so much. Bye-bye.
You're welcome.
Bye.